All right. So last time we were talking about reactions with carboxylic acids, and the theme was that carboxylic acids have this acidic proton. That's why they're called acids, right? And what this means is that you can't use a really strong base to attack the carbonyl carbon. For example, OR minus would not work because it would instead just pull a proton off the carboxylic acid. So we discussed how you can use a catalytic acid to protonate the carbonyl oxygen to turn it into an oxonium ion that's reactive enough for a neutral alcohol to attack. Then it attacks the pi star at the carbonyl carbon. We break the pi bond to get a tetrahedral intermediate. We use the conjugate base of our acid to convert this ORH plus group into not a good leaving group so that it can stick around, and then we use our acid to protonate the OH group to turn it into water as a leaving group, which is a good enough leaving group for this neutral oxygen to kick electrons down and kick the water off. All of these are equilibrium steps, and we're using the fact that water leaves as a way to push the equilibrium forward by removing water either with some kind of hygroscopic salt or by distillation. Finally, we regenerate our acid excuse me, by deprotonating this oxonium ion that gives us the ester. Okay, we called that Fischer esterification. At the very end of class, I mentioned that you can do this backwards if you use an excess of water, use acid in the presence of water, and you can push the reaction back to the carboxylic acid. And I mentioned I'm not going to show you the mechanism for this because the intermediates are exactly the same as for the forward direction, only you would have to push arrows that get you from here to this intermediate. And the bonds that you form tell you what arrows you need to push, right? How do you get a proton on the oxonium ion? Well, lone pair electrons from this carbonyl attack the acid, the proton of the acid, to give you these products and so on. So one good way to practice the Fischer esterification reaction would simply be to try to do the hydrolysis reaction, and go ahead and give that a try, and I believe it's shown for you in your text. There's another way you can hydrolyze esters, and this one is important for historical reasons. If you take an ester and hydroxide, you can attack the carbonyl carbon directly to get a tetrahedral intermediate. If this tetrahedral intermediate collapses to kick off OR minus, or sorry, OH minus, you're just going back to this previous step. But what drives this reaction forward is that if you kick off the OR minus group, you are immediately left with, as products, your carboxylic acid and this alkoxide, which is a really strong base and very able to remove a proton from the carboxylic acid. And this is irreversible in the sense that the equilibrium constant is like a gazillion because the pKa of this proton on the carboxylic acid is around 5. The pKa of that proton on the alkoxide is, or on the alcohol, is like 16. And so products are favored here by a factor of like 100 billion. So this reaction goes all the way forward. Excuse me. And of course, if you want the carboxylic acid instead of the carboxylate, you can gently adjust the pH and acidify it to get the carboxylic acid out. That's a minor detail that I don't ask you to worry about. But this is called, this reaction, ester hydrolysis under basic conditions is called saponification because it's the process our ancestors used to make soap. So I want to tell you that story briefly because it has a lot to do with biology and history. Fats and oils are a class of molecules that are known as triglycerides. They're called triglycerides because you have this 3-carbon triol where each of the alcohol oxygens, this 3-carbon triol is called glycerol, and in the triglyceride, each of those is linked to a long chain carboxylic acid. And these chains can vary in length. They always have even numbers of carbons for reasons that we will talk about later. But you've got this sort of nonpolar tail, and this is what makes fats and oils nonpolar and not miscible with water. It's why oil and water don't mix, right? So our ancestors discovered that if they mixed animal fat with something called lye, and lye is just potassium hydroxide, which you can get from wood ashes. So if any of you have read about or been to Kirtland, Ohio, one of the restored properties there is what's called an ashery, where they burned wood and generated ashes. Why did they want ashes? Because you can get potassium hydroxide from wood ashes, and then they would use that to make soap. So how does this process work? Well, it works exactly the way you would expect. The hydroxide attacks one of the carbonyl carbons of the glycerol molecule. From this point on, if it's okay with you, I'm going to abbreviate. Except with the long hydrocarbon chain. Oh well. Then lone pair electrons, just as we did above with ester saponification, can kick off. And this is the glycerol portion of the molecule. Can kick off the glycerol alkoxide. Kick off the glycerol molecule with one of its oxygens negatively charged. And then what happens immediately thereafter is the negatively charged oxygen from glycerol removes a proton from the carboxylic acid. And your product ultimately is this long chain carboxylic acid in its conjugate base form. And then ultimately you have the glycerol molecule that's liberated as well. I actually don't know whether soap makers in the 19th century did anything with glycerol or not. So what does this have to do with soap? Well, and so what I've tried to show you is this here is just an example of the general saponification reaction. But the reason it makes soap is because this long chain fatty acid is what it's called. Kind of rude, but okay, whatever. And the long chain fatty acid has a carboxylate that's negatively charged up at the front. And this is sort of a polar head group, and then it has a non-polar tail. And of course, the polar head group is going to be able to interact with water, but the non-polar tail will not because of the hydrophobic effect, which you learned about in 351. Now, the shape of this molecule, if you sort of think about it, is kind of conical, right? And so these molecules in the presence of water self-assemble in order to sequester the non-polar tails from water. They arrange themselves in sort of a spherical pattern, which I think you saw before in 351. wherein the polar head groups are all exposed to water. And this assembly, this spherical assembly, is called a micelle, whereas the nonpolar tails are all sequestered from water in the interior. And the reason this works as soap is because nonpolar molecules that you might have on your skin, oil, grease, other things, can be solubilized in water because they can fit inside these micelles and then be carried away with the water. So if you've ever tried to wash, I don't know, vegetable oil or margarine or butter off your hands in just water, it doesn't go very well. You mostly smear it around. You put soap there, soap forms micelles in the water, and then the oil and dirt kinds of molecules can be carried away. All right. Any questions about soap? Okay. Just a couple other things to do with these triglycerides. It turns out if you remove one of the two fatty acids, you have something that's called a diacylglycerol. That's abbreviated as DAG, and you may have seen that in other biology or cell bio type classes. But interestingly, if you nature can take these diacylglycerols with the long fatty acid tails, and it can modify the remaining oxygen in a phosphoester or a phosphodiester with some other kind of polar group. So what I've drawn here would be something like phosphatidylcholine, which is a component of membranes. It has the same sort of structure, basic structure as a micelle. You have this polar, as a soap molecule or the fatty acid, you have this nonpolar tails here and then a polar head group here. Hold on just a second. And if you look at the overall shape of this molecule, instead of being sort of conical, it's more cylindrical in shape. That may be difficult to see if I don't sort of draw out what these R groups are. I think that's a 16 carbon chain. There are, they vary, but 2, 4, 6, 8, 10, 12, 16. Anyway, the chains, the fatty acid chains in these molecules vary in length. But the overall shape of this is sort of cylindrical. And what that means is instead of assembling in a sphere, and this is maybe how you have seen these lipids portrayed in other texts, you sort of have a polar head group with two nonpolar tails. And each of those has a sort of cylindrical shape. In order to sequester the nonpolar stuff from solvent, what happens is these, like the fatty acids, line up side by side. But because of their cylindrical shape, there's not as much curvature. And so in order to fully sequester the nonpolar things from water, you have another sort of stripe of these lipid molecules. I wanted the whole thing. That pack on the other side And this generates what's called the lipid bilayer, which is the basis for biological membranes. This lipid bilayer can extend sort of indefinitely in sort of front and back in a planar sort of direction, and eventually that plane can fold back on itself and you get a vesicle or a cell membrane. This would be called like the inner leaflet, and this would be called the outer leaflet. If this were a cell membrane, this would be extracellular matrix, and this would be like cytosol. Okay, so that's another important aspect of ester formation. I want to show you briefly how biology deals with hydrolyzing these esters. Naturally, though we can do it in a big kettle over a fire using lye, those aren't necessarily bio-friendly conditions. And so nature has evolved a way to hydrolyze these lipids with a class of enzymes that are called lipases. So what I'm going to show you now is something you'll see again in biochemistry. It will be challenging for you to look at what we're talking about and find the common elements with things that we've talked about before without getting lost in the details. What were the names around the lipid bilayer that I drew? Inner leaflet and outer leaflet. That's terrible penmanship. That's not important, but you'll hear some biology classes talk about that. Sometimes the lipids in the inner leaflet are different from the lipids on the outer leaflet. Another interesting thing is molecules that need to cross this membrane somehow have to get through the polar stuff and through the non-polar stuff and through the polar stuff again. And that's why there are so many membrane transport proteins for importing and exporting different things through the membrane. A lot of useful small molecule drugs, though, will be taken up by the cell via passive diffusion, which means they can actually get inside the membrane. Okay, so lipases, what are these enzymes? These are enzymes that hydrolyze lipids, and one thing you need to understand about enzymes is enzymes make reactions faster by making the transition state more stable. That will lower the energy of the transition state and make it easier to go for the first step or the rate limiting step of the reaction to occur. So I'm going to draw an abbreviated form of our lipid. Understand that this portion is the fatty acid portion. Understand that this portion is glycerol. Lipases have a spot into which the carbonyl oxygen packs. And this spot is lined with hydrogen bond donating groups. They happen to be amide protons from some of the amino acids in the protein, but their specific identity isn't important. But this creates sort of a little pocket that oxygen, carbonyl oxygen, can hydrogen bond with. And that hydrogen bonding activates the carboxylic acid towards attack. Before, when we were hydrolyzing esters under acidic conditions, we talked about needing to protonate the carbonyl oxygen so that water could attack, right? And we're sort of doing the same thing here, only we're not fully protonating the carbonyl carbon. Now, nature doesn't use water as the nucleophile initially, and there are a lot of why questions in terms of why nature chose this option versus others that I'm not sure I understand. But what actually catalyzes the reaction is very well understood. This alcohol side chain is called serine. Then there's a related side chain called, there's a nearby side chain called histidine. I don't care that you memorize these side chains. And then near the histidine is a side chain called aspartate, which is the conjugate base of aspartic acid. Okay? And the way nature's going to do this is first we're going to have the cysteine oxygen attack the carbonyl carbon. We're going to get a tetrahedral intermediate, and then glycerol is going to leave. At that point, we will have this long 8-chain acyl group attached to serine, and then we'll bring in water to hydrolyze that linkage. The problem is that serine itself, neutral serine, is probably not nucleophilic enough to attack the carbonyl carbon, even if we're hydrogen bonding with that carbonyl carbon. And so that's where these other two amino acids come in, histidine and aspartate. These are going to act like assistants for making the serine nucleophilic enough to attack the ester. So the histidine side chain, lone pair electrons here, will pick up a proton from serine, and then the resulting serine alkoxide will attack the carbonyl carbon to give you a tetrahedral intermediate. The thing that allows the histidine to remove a proton from serine is this aspartate group, who can pull a proton off histidine and make the histidine nitrogen more nucleophilic. This group of 3 amino acids is called a catalytic triad, and it's used all over the place, even in other enzymes, when you want to do hydrolysis of ester or amide bonds. And it basically acts as a proton shuttle in the sense that we need to get rid of that proton to make serine a good nucleophile. And in order for histidine to be able to do that, we need to get rid of this proton. So after that attack has happened, I'm going to redraw I want you to see what the side chains look like after we've done that attack. I'm going to sort of abbreviate what's in the oxyanion hole. You can see why it's called the oxyanion hole, because it stabilizes the tetrahedral intermediate. So after serine attacks, it is bonded to the carbonyl carbon in a tetrahedral intermediate, and that negatively charged oxygen is hydrogen bonding with that with the oxyanion hole. And the other side chains, let's look at what they look like. This is what the histidine looks like, and this is what the aspartate looks like. It's now in its conjugate acid form. And the proton that used to be on the serine is now on the histidine. The proton that used to be on the histidine is now on the aspartate. One question that you can ask at this point, and this is a question best reserved, I think, for a biochemistry class, but histidine in and of itself should not be a good enough base to remove a proton from a carboxylic or from an alcohol, because the pKa of an alcohol is 16, whereas the pKa of the conjugate acid of histidine is 6. So you would think that this type of proton transfer would be unfavorable by a factor of 10 billion. Similarly, you would not necessarily think that aspartate would be able to remove a proton from protonated histidine, because the pKa of the carboxylic acid, once you get a proton on it, is around 4 to 5. So histidine should be a stronger base than aspartic acid. So if that reasoning is a little bit clouded to you, that's fine. I'm just pointing out that the fact that this is actually happening is somewhat unusual, and it's still something of an element of controversy as to why this can happen. One potentially good explanation that I like is just that the enzyme active site is not in water per se, but is a more nonpolar environment, and pKa's change in nonpolar environments. And so perhaps the environment adjusts the pKa's of these protons such that this kind of proton shuttling is possible. The alternative explanation is that these side chains are close enough to each other that actually these aren't really proton transfers so much as they are really, really tight and close hydrogen bonds. And both of those are things that people think about. It's not important for this class, but I wanted you to be aware of the issue. Once we get here to this tetrahedral intermediate, electrons can kick down and kick off the glycerol group. Remember, this is our glycerol group. This is our long chain. Oops, I wanted that to be green. This is our long chain alkyl group. As that glycerol group is leaving, as it's leaving as a negatively charged alkoxide, it picks up this proton from histidine, and then we do the proton shuttle again so that histidine can pick up the yellow proton from aspartic acid. Oops. So after this step, what you've got now is a new ester. This is the serine side chain. This is your long chain carboxylic acid tied up in an ester linkage with the enzyme. And then you've sort of reset the other two residues of the catalytic triad in the sense that now we're back to conjugate base of aspartic acid. The yellow proton is now on the histidine, and glycerol left, but with it leaving, it took the blue proton. So far, you may be thinking this is convoluted because it doesn't look like ester hydrolysis at all. All that we've done is swapped out one alcohol, which is the glycerol portion of this molecule, for another alcohol, which is serine. So notice now we still have an ester, only this time it's bound. The ester involves an amino acid side chain in the enzyme. So far, this is just what we would call transesterification, meaning you transfer a carboxylate group from one alcohol to another, but the starting product's an ester and the final product's an ester. The hydrolysis step comes next, and we're not actually going to go through it in a lot of detail because it basically follows what we have done so far. A molecule of water enters the active site, and we're going to install a new blue proton on the histidine side chain. So histidine will remove a proton from water. The resulting OH minus will attack the carbonyl carbon to give us a tetrahedral intermediate. At the same time, aspartate will remove the proton from histidine. Oops, I am so sorry. I think I drew the wrong structure for histidine. At the same time, aspartate will remove the yellow proton from histidine, and that will get us to an intermediate, which I'm just going to draw briefly, tetrahedral intermediate, in which now we're going to be able to collapse and kick off the enzyme alcohol group as a leaving group, and our carboxylic acid can leave. Okay, I haven't shown you what the remaining other residues look like, but the arrows will show you what to draw here if you want to, and you can look in your notes up here for what happens. Okay, so nature is using these steps all the time. These steps of, can I attack the carbonyl directly, or do I need to activate it first? Then what's my nucleophile? I attack to get a tetrahedral intermediate. Then what happens next depends on whether or not there's a good leaving group. And so in this way, enzymes have been doing all along what we have just been learning about. Okay, I want to pause for any questions you might have at this point. Okay. Well, if you continue, if you have anything, let's see. Where did the added OH group come from again? Water. A molecule of water enters the active site. And then the catalytic triad activates it to be a nucleophile. Anything else? For the reverse proton shuttle, does that seem to be favorable looking at the pKa's? Yeah, you probably would expect an alkoxide. Yeah, I guess the reverse, that's an interesting question, Craig. For the reverse, you might expect an alkoxide to be able to deprotonate histidine, and you might expect histidine to be able to deprotonate an aspartic acid. So maybe that's one of the reasons why it's so efficient. You can go uphill versus downhill. Note that enzymes don't change the thermodynamics of the reaction, but rather just bind the transition state and accelerate the reaction. Yeah, those are good questions. What else? Okay, so we started today by talking about carboxylic acids and how they're difficult because you have to deal with the presence of that acidic proton. This is why you couldn't make an ester by bringing an alkoxide, negatively charged alkoxide, into the presence of a carboxylic acid. And the same is true for other types of compounds that you might make. For example, if I wanted to take this amine and react it with the carboxylic acid to give me an amide and then water, that's thermodynamically favorable, but it doesn't happen. And the reason it doesn't happen is it's more thermodynamically favorable and faster for nitrogen, which is a base, to remove a proton from the carboxylic acid. At that point, you have the negatively charged carboxylate, which is no longer an electrophile. It's not an electrophile because it's actually negatively charged. It's got extra electron density. And then over on the amino side, you now have the corresponding ammonium ion. And that's just acid-base chemistry. It's fast. If you compare pKa's of conjugate acids, there's a sense for how thermodynamically favorable it is. And so then you're sort of done. You're sort of dead. Your text points out that in some cases you could take this mixture of the carboxylate and the ammonium and heat them to really high temperature, and then they might spontaneously form the amide and release water. I have never done that reaction. I don't think it works for most carboxylic acids and amines, especially not for complicated molecules where elevated temperatures like 300 C are a problem, right? And can result in degradation of the molecule. We make amide bonds all the time in my lab, and we never do it via the heat the carboxylate ammonium salt. So I'm going to show you sort of two workarounds that allow you to make amides from carboxylic acids. They're basically substitution reactions in that we're going to replace the OH group on the acid with an amino group on the amide. But the approach is going to be to first convert OH into something that's a good leaving group that doesn't have any acidic protons. So strategy one involves making an acid chloride. So your text introduces this reaction. It's a reagent that may be familiar. That is thionyl chloride, or SOCl2. SOCl2 looks like this, and that will convert the carboxylic acid into the acid chloride. And in some ways, this is analogous to a reaction you saw, I think, in the alcohols chapter of 351, where you did use SOCl2 to turn an alcohol OH group into a chloride, substitute it with a chloride. The mechanism isn't the same as conversion of an alcohol into an alkyl chloride. I'm not going to hold you responsible for the mechanism. I'm going to draw an intermediate in that process to give you a sense for why this reaction works. Again, this is for your edification, and because for me, I feel like if I don't see at least some of the mechanism, I don't really understand the reaction. So before this point, this is an intermediate, sort of a few steps in. Before this point, we've deprotonated the carboxylate oxygen, and it has attacked the sulfur of SOCl2, and then chloro has left. And that gives us the following intermediate. And electrons can kick down and kick off this whole group. And that may not look particularly like a good leaving group, but here's why it is. As it's leaving, as a negative charge is building up on that oxygen, electrons can actually kick down here and kick off the chloro group. That gives you your acid chloride plus SO2, which is a gas and bubbles off. So this is irreversible and driven forward, and then Cl minus as a byproduct. So we're not worrying about the mechanism of this reaction. I just wanted to show you this. But the effect is to replace the OH group with a leaving group like Cl minus, or Cl, that is like chloride, that is a good leaving group, in fact a better leaving group than OH minus, but doesn't have an acidic proton. At that stage then, the second step would be to take your acid chloride and then do the substitution reaction with your amine. Now, I will show you the mechanism of this reaction, but it should look familiar, and you should be able to sort of figure it out on your own at this point. The acid chloride is reactive enough for the neutral amine to attack directly. Now, before, we would have thought about using an acid catalyst to activate the carbonyl for attack by a neutral nucleophile. We can't use an acid catalyst here because our amine is a base. And so fortunately, and would just deprotonate the acid, and then you'd be done. So fortunately, the acid chloride is reactive enough for the direct attack to occur. Attacks the pi star, you break the carbon-oxygen pi bond. Nevertheless, if you, in drawing this mechanism, think, oh, shoot, I need to protonate that oxygen first, and you do so, I'm not going to penalize you. Excuse me. The product that the intermediate that we get from that step looks like this: negatively charged oxygen, Cl, and then a nitrogen bonded twice to hydrogen and then once to carbon with a positive formal charge on nitrogen. Chloro is a good leaving group, but so is the amine this ammonium group that's positively charged now, and so we need to do a proton transfer to get to remove one of those protons so that the amine turns into not a good leaving group. Your text points out that to do this, we're actually going to use an excess of the amine, so that the second equivalent of the amine acts as a base to deprotonate the nitrogen. At this stage, that you have a tetrahedral intermediate where there is only one good leaving group, which is this Cl minus, and then you have not a good leaving group here. Electrons on the negatively charged oxygen kick down, leaving group leaves, and that generates your amide product. You have Cl minus as a leaving group, and then as a byproduct you have the other protonated part, the positively charged ammonium group that you get from doing this proton transfer. Okay, so that's step one. Questions you want to ask about that? If there is an alcohol present, would you use TBDMSCl to protect the alcohol to avoid the substitution reaction of your alcohol with the chloride? Yeah, that's a great point. I hadn't thought about that, but you're absolutely right. If you were doing a reaction of a carboxylic acid where there was also an alcohol functional group, you would want to protect the alcohol as the silyl ether first so that it would not be involved in the reaction with SOCl2. Great point. Okay. So as I said, we make amide bonds in my lab all the time, and we basically don't use this thionyl chloride method because the reagent is, I think, pretty reactive, and in many cases acid chlorides themselves are too reactive and can react with other functional groups in the molecule. So instead, we use something akin to approach number 2, and that is to use something that's called a coupling reagent. The coupling reagent is going to replace is going to transform the OH group into a good leaving group that lacks an acidic proton, but it's not going to be as reactive as the acid chloride or prone to the same sorts of competing reaction issues. The reagent is something that you're probably going to hate. It's the following: a carbon bonded, doubly bonded to 2 nitrogens. This is like a carbon that's involved in 2 imines. And then each of those nitrogens is bonded to a cyclohexane group. This reagent is called DCC, which stands for dicyclohexyl carbodiimide, with 2 I's adjacent to each other. It's really kind of terrible, and I'm not going to care that you know that name. DCC is sufficient abbreviation. You also need a non-nucleophilic base. You want it to be non-nucleophilic because you don't want it to attack the carbonyl carbon. And a good non-nucleophilic base of choice is triethylamine. As a tertiary amine, it's sterically hindered a little bit, and then it's not a good nucleophile because even if it did attack a carbonyl carbon with a good leaving group here, once you got to that tetrahedral intermediate, there'd be no acidic proton, no proton to remove to get to the neutral nitrogen, and so this is just going to fall right back off. Okay. So I want to show you the mechanism of this reaction, again, not because I want to test you on the minor details, but rather because I feel like if you don't see it, it may not, if you don't see the mechanism, it may be difficult to remember what happens. Question from Craig: would potassium tert-butoxide work? That's a good idea in that it's a sterically hindered base. My guess is tert-butoxide would start to react with a carbodiimide reagent, which is an electrophile. So you want a base that's moderate enough to deprotonate a carboxylic acid, but perhaps not strong enough to attack a carbonyl. Okay, so first step of the reaction is we use our non-nucleophilic base to deprotonate the carboxylic acid, thereby giving us the carboxylate, which is now a nucleophile. And we're going to use this strange reagent as an electrophile. The LUMO of this molecule is probably two equal in energy low-lying orbitals, which are the carbon-nitrogen pi stars. We can attack either one of them, not both, but we attack the carbon and carbon-nitrogen pi star. That breaks the carbon-nitrogen pi bond. And then that generates an intermediate that looks like this. And then this negatively charged nitrogen picks up a proton, probably from our triethyl ammonia molecule that we make when we deprotonate the carboxylic acid. At this stage, we get something that looks, from a certain point of view, like an anhydride in the sense that you have two sort of carbonyl carbons attached to each other via an oxygen. And you can think of all of this as a good leaving group for reasons that I'll show you in a minute. So at that stage, your amine can attack the carbonyl carbon to give you a tetrahedral intermediate, which looks like this. And now what I'm going to show you next is how the leaving group leaves. It's not hugely important, and I think it bothers some people, but it's kind of cool, so I thought I would show you. It turns out that, do you remember how after the nucleophile attacked the carbon of the carbodiimide, we got a negatively charged nitrogen that we had to protonate? If we have this oxygen kick down and kick off the leaving group, we're going to get another negatively charged nitrogen. But in this intermediate, the negatively charged nitrogen happens to be very close to that proton on the positively charged ammonium group. In fact, they're sort of in a six-membered hydrogen bonded ring, or rather 1, 2, 3, 4, 5, 6 atoms apart. And six-membered ring transition states are pretty favorable. So it's actually permissible and okay for us to have the leaving group leave and have the leaving group pick up a proton from the positively charged nitrogen, all in the same step. If you then want to draw the byproduct that our coupling reagent turns into, it is called dicyclohexylurea. A urea is a molecule that has a functional group like this, where a carbonyl is bonded to two nitrogens. But you make your amide, and then you make your very inert urea molecule, which is very stable and easy to separate from the amide. Okay, so what do I want you to know from all of this? In particular, students are often worried as to whether they need to know all of this. This is for your enrichment. I want you to understand generally what's happening. Nucleophile, we convert the OH into a good leaving group by deprotonating it, and then that attacks the carbodiimide reagent, or DCC. Once you've got a good leaving group, the amine can attack to give you a tetrahedral intermediate. The positively charged nitrogen needs deprotonating so it can stay, and the leaving group leaves and picks up a proton on its way out, and that gives you the amide. And this kind of chemistry we use all the time in my lab, in the Michaelis lab, in the Castle lab. Amide bond forming reactions work really, really well, and they're really important because proteins consist of amino acids that are linked together via amide bonds. And so next time we're going to talk about how biology makes amide bonds using the ribosome and tRNAs, and then we'll also talk about how beta-lactam antibiotics work. We will likely spend our time on the more difficult topics and some of these biological applications. Some of the more simple reactions, that is converting acid chlorides or anhydrides into esters or amides or carboxylic acids, that's pretty easy and straightforward. So we won't spend much time in class on that. All right, so we're out of time. Thank you, and I hope you have a good day. I will let you know if we need to do Monday's lecture via Zoom. We'll see you guys later.